today we're going to focus on mainly problem solving. So we'll look at sort of 3 different scenarios where we're looking at these lead questions, sussing out the details of what the data is telling us, and try to propose structures. And then the last half of the lecture will sort of put it all together where we're given INR, mass spec, and NMR data, and asked to come up with a structure based on what each instrumental technique is telling us. So at this point, we should be comfortable with extracting that information from IR, mass spec, and NMR. Get some clues, put the clues together, and make sure that we're sort of self-sufficient and that we're not proposing something that would violate what the data is telling us. Any questions before we get started? So we'll look at propane in this problem in relation to what we were talking about last time with why proton NMR's signals have multiplicity to them. And so the signal of interest is dependent upon the number of neighbors to those hydrogens attached to whatever carbon we're looking at. And so on Friday, we'll get to the theoretical reason of why multiplicity happens, but today we're just applying the N+1 rule. And so we'll look at propane to start, and then we'll go through some more complex examples of that. So propane, there's the word, here's the structure, and so we can represent it like that. So again, that is stuff from Module 1 that we should all be comfortable with now. Again, hydrogens attached to carbons are implicit. Hydrogens attached to heteroatoms always need to be shown. So it's a hydrocarbon, it's CNH only. And the question here asks, how many unique signals do you expect in the proton NMR? So there should be 2. So CH3, CH2, CH3. We can see that there's a line of symmetry that bisects carbon 2. And that renders the CH3 groups on carbons 1 and 3 equivalent. Then the CH2 group or methylene group is its own thing. So we would say there's 2 unique sets. And so when we say that set, we're really talking about the signals that we should see in the NMR. And of those 2, we need to supply 2 numbers now in the parentheses, the sum of which is the total number of hydrogens in the molecule. So what should those numbers be? So 6 and 2. And so, conceptually when I call that the ratio, in the actual proton NMR, we call it integration. And if you go into more analytical chemistry or biological science courses that use instruments, integration is a common term. The computer does some math, and really what it's doing is calculating the area under the curve of interest, and then it sort of finds a ratio for you, and we'll show that a little bit later today with some of the data we look at. So we have 2 signals, the ratio of 6 to 2. And so the next question is, our first approximation is there's two signals. Now we want to predict how they're going to look like. So remember that the CH3 groups will integrate to 6, the CH2 group will integrate to 2. And so now we need to apply this n+1 rule to predict what the signal is actually going to look like. So again, because these CH3 groups are the same, they have one neighbor, the CH2 group. So applying the n+1 rule, what should that signal look like? How many lines should it have? So it should have 3 lines, and we would call that a triplet. And then the CH2 group has how many neighbors? Hydrogen neighbors. 3 plus 3, 6 plus 1, 7. So that's going to have 7 lines. And for lack of a better word, we'll call it a septet. That's kind of rare because when you start counting these neighbors, it's pretty rare that you get past like 4 or 5. So this is, a pretty simple molecule. You have 6 neighbors. So that's going to be a septet. And a review of, of these two signals, where should they fall? If we're predicting on the chemical shift scale of parts per million, we're going to use methane at 0 as our benchmark. So the methyl groups look more like methane. So as you're reading from right to left, increasing chemical shift, you should see that triplet first. So I'm just going to abbreviate it T. And then the CH2 group, you've done 2 carbon substitutions. So it should be at a greater chemical shift than the CH3 groups. So that gives you about an approximation of where you should see these things. So the CH2 group we just went through. So has 6 neighbors. So we apply the n+1 rule, we get 6 plus 1 equals 7, and that will be the septet. And the other thing that we'll talk more about on Friday again is the intensity of each line in the multiplet. Again, that arises from Pascal's triangle, which is due to the combinations of spin states that you can have. So the reason that these things become complex is that each hydrogen atom can be a spin of +1/2 or -1/2. And so the signal of interest feels those spins from the neighbors. So it's communicated through the bonds. And that ultimately leads to the number of lines in the distance between the lines. So there's a couple more things that we have to progress through before we fully understand why proton signals look the way they do. So here is the spectrum of propane. This is a simulated NMR. So simulated or computed. So it looks nice and perfect. Normally NMR spectra don't look this nice. So basically the app, let me see what that, I think you can get it for free if you have an iPhone. I think it's called Orange NMR is the free one. It'll let you draw 10 free molecules before you have to pay for it. I don't know how much it costs. I got it for free because I'm an instructor, but this is what I use to draw the things that you see on your exams, basically. There's other, if you go on Canvas, there's other web pages that are linked there that'll take you to more problems you can do. And there might be one that can simulate spectra for you as well if you draw the structure. So here we see the two signals. So there's one, and there's the other one. It's kind of hard to see, but I think this says 0.9 is the chemical shift there. So that's closest to 0. And then this is like 1.3 or something. So it's shifted at a higher chemical shift. And we stated before that these would belong to the CH3 groups. And then this would belong to the CH2 group. The other thing that's not shown here is that integration. And typically on an actual spectrum, the integration is shown sort of below the signal. And so that triplet is worth 6 hydrogens. And then the septet is worth 2 hydrogens. So it's a triplet because we count 1, 2, 3 lines. And then the CH2, which is a septet, the first line is really tiny, but it's right here. So 1, 2, 3, 4, 5, 6, and 7. So now, if you kind of think backwards in a sense, say you were not given the name or the structure. And if you looked at this signal and you counted those 7 lines, you would just say 7 minus 1 is 6. So therefore, the attached hydrogens there must have 6 neighbors. That's another way to think about it. For this one, 3 minus 1 is 2, so that has 2 neighbors. So again, just make sure that you're keeping straight that the multiplicity arises from the neighboring hydrogens. Any questions? So of the uniqueness set, the first number is telling you the number of unique carbons. This number is telling you the number of unique hydrogens, but number of signals, that's what it's equivalent to that you should see. the ratio in that parentheses is the integration of those signals. So that the next layer that, again, you want to be clear on so how do the signals look? Called multiplicity. And that is due to the neighbors. So if you're looking at the structure, you can theoretically predict it, or if you're looking at the actual spectra, at that point you sort of have to do n minus 1 to get you the neighboring information. So I think there's two sets of problems like this, and then we'll get into the one where there's, all of the data. So if we're given a molecular formula of C3H7Br, and then we're given that data, what is the structure, and then what's the name of that structure? Let's do the normal first thing is calculate any degrees of unsaturation. So we know that halogen atoms will increase the H count. So this becomes C3H8. So N equals 3, 2N plus 2. That's 6 plus 2, that's 8. So in theory, it should be C3H8, so there's no degrees of unsaturation. So we have 3 carbons. We have to bond all of them together. And then at some point, stick a bromine atom back in. So there's 3 carbons. We'll do the logical thing and put the bromine at position 1. So there's one possible structure. Or we can put it on carbon 2. And so for that molecular formula, that's the only 2 structures you can draw. And so now let's determine the unique sets, unique carbon and hydrogen sets, and then we'll go look at the data and see which one matches. So for the first one with the bromine on carbon 1, how many unique carbons does that have? So 3. How many unique sets of hydrogens does that have? So 3. And then we need to supply the ratios there. We'll just march along the chain 2, 2, and 3. So for the 2-bromo compound, how many unique carbons does that have? So it has 2. And then the unique sets of hydrogen. So 2 as well. And that ratio should be 6 and 1. So now that we've figured out that, we can then go look at the data and see which one matches. So we're given the chemical shift in parts per million, splitting or multiplicity, and then integration or ratio. So what this is telling you right here, there's 2 signals, so that's 2 unique sets of hydrogen. And then the integration is telling you the ratio. And so we can see that it's got to be the 2-bromo compound. And then how do we account for the splitting? So it says at 1.71, so again, that's close to 0, so those are the methyl groups here and here. They most resemble methane. So 3 and 3, that's your 6. There's one neighbor, so 1 plus 1 is 2. That gets you your doublet. Then notice this big jump in chemical shift, 4.32. That's because the carbon atom is bearing an electronegative element. So that really pushes it, way past the other signal that you see. So you have 1 hydrogen, you have 3 plus 3, 6 plus 1, that's 7. So that signal there will look like a septet. Any questions before we move forward onto another molecular formula? It's the 2-bromopropane. So sort of same logic here. So C4H9Cl. Yeah. So C4H9Cl. And what we'll find with this molecular formula is that we have more constitutional isomers we can draw. And then we're going to go through the same exercise of uniqueness and see the questions presented in different ways. So chlorine will add to the hydrogen count. So we have N equals 4. So 2 times 4 plus 2, that's 10. So there's, again, going to be 0 degrees of unsaturation. So again, that's telling you something as well. There's no sp2 or sp hybridized carbons. There's the chlorine. So you're only going to see the CH signals in a certain region of the proton NMR. Like, for example, you're not going to see anything from 5 to 12 because there's no sp2 or sp hybridized carbons. So how many constitutional isomers are there? And again, the way we set this up, we'll say for carbon count 4, we'll just start drawing the linear constitutional isomers. Then we'll knock it down to 3 and start drawing branched ones. So there's 4 carbons. Again, no degrees of unsaturation. We got to stick a chlorine in there, so we'll put it at carbon 1. So this would be called 1-chlorobutane. Another isomer, we'll stick it on carbon 2. That's 2-chlorobutane. So you can't stick it on carbon 3 because really all you're doing is just redrawing the 2-chloro isomer. And the same for carbon 4, you're just redrawing the 1-chloro. Now if we start with the 3-carbon is the longest chain, we now have to put back in two things, a chlorine and a CH3 group. Let's start with the CH3 group. So that can only go on carbon 2. If you put it on 1 or 3, you're just drawing the other 2 we already did. And so now we have chlorine. We'll put it on carbon 1. So this would be called 1-chloro, 2-methyl propane. And so the answer is 4. So the last constitutional isomer we'll draw, we're just going to put the chlorine on carbon 2. So this is 2-chloro, 2-methyl propane. So now we have 4 constitutional isomers, and the next series of questions are just asking in different ways about each of them. So there they are right next to the names. And so this question asks, which one has the NMR data shown? Any guesses before we walk through it? I heard an A. Don't think so. Say it loud, say it proud. C. So we'll go through C and then we'll go through the rest of them. And then that will help us answer the rest of the questions, basically. So how many unique carbons does C have? So 3. So the methyl groups are the same. That's 1, the methine, and then the methylene. Because there's no carbons without hydrogens, you're still going to get 3 unique sets of H. And that ratio is going to be 3 plus 3 is 6, the 1 and the 2. And so once you figure that out, you can just match it to the data that you're given. So again, what this is telling you is the total number of signals, their chemical shifts, the ratio or integration. And then again, the splitting is probably the most sort of difficult thing to interpret, so you kind of leave that for last. But I assure you that when we walk through A, B, and D, they're all different, and they're not going to match the data that you see. So the 1-chlorobutane, choice A, has how many unique carbons? So 4. Again, the unique sets of H will track that. And then if we just count, starting from carbon 1 down to the chain, that's how we'll write the ratio. 2, 2, 2, and 3. So the 2-chlorobutane has 4 unique carbons, therefore 4 unique sets of H. So you might think, well, how do I differentiate them? It's going to be the integrations will be different. So again, we'll start at carbon 1 and then just work down the chain. 3, 1, 2, and 3. So you can see right there that ratio or integration is different. And so you would be able to tell that they're different spectra. So choice D, how many unique carbons does that have? 2. How many unique sets of H? Just 1. So now notice, again, those numbers are different because that central carbon no longer has H's attached to it. Since it's one number, we have 3 times the 3 methyl groups, so that's going to be 9. So overall, through this exercise, even though you're given one molecular formula, after you draw the constitutional isomers and figure out the uniqueness, you can differentiate them. And I don't want you to think that you're just like rowing the boat out into sea for no purpose. The purpose of this, when you start learning reactions, for example, in one of the first reactions you'll learn, say we'll take butane, and we're going to treat it with chlorine and light. It's going to take a hydrogen off that butane and substitute it for chlorine. And so you can get either the 1-chloro or the 2-chloro as products. So if you end up with 2 products from a reaction mixture, how do you differentiate them? And that's the point of this exercise. Furthermore, the uniqueness set of hydrogen is very important, because if you can form these 2 things, they don't form in a 1-to-1 mixture. One's going to be a major product, the other one's going to be a minor product. And it's important for you to understand unique hydrogen sets and also what they're attached to, methyl, methylene, or methine. All of that information will lead you to predict what the major product of a reaction will be. So we took out one of them. So I think we said the last one was C. This one is asking you which one has a single peak in the proton NMR. And so that was answer D. Where you had the 3 methyl groups. So you have 1, 2, 3 methyl groups. They're all the same. There's a carbon. There's no hydrogen neighbors. So that signal remains a singlet. For 2-chlorobutane, as shown, the Roman numerals are just numbering along the carbon chain. And the question is asking you, how should the signals attached to those Roman numerals occur? And so now again, what you have to consider is look to the right, to the left, up, down for any neighbors, count them, add 1, and then that's how you get your multiplicity. So this CH3 group, how many hydrogen neighbors does it have? Just 1. So 1 plus 1 is 2, that's a doublet. So we can eliminate A and D. Carbon 2 has 1 hydrogen. How many total neighbors does it have? So 3 plus 2 is 5. 5 plus 1 is 6. So it looks like we're going to eliminate this now. And then B will be the correct choice. If we verify carbon 3, that has 4 total neighbors. So 4 plus 1 is 5, that's the pentet. And carbon 4 is a CH3 group. It has 2 neighbors. 2 plus 1 is 3, that's your triplet. And so the one question for the last isomer, which was 1-chlorobutane. We have the choices shown above the signals A, B, C, and D. It says, what signal corresponds to hydrogens bonded to carbon 2? B, is everyone on board with that? So carbon 2 is a CH2 group. Now when we count the neighbors at 1 and 3, 2 hydrogens plus 2 hydrogens is 4, plus the 1, that's 5. So let's count here. 1, 2, 3, 4, 5 lines, so that's the pentet. So A is going to be the CH2 group on at position 1. See this big gap here from that triplet to that pentet, that huge chemical shift difference? Again, that's due to that chlorine. So it's sitting out by itself. It's the one that looks the most different from everything else. Then you have this cluster of 3, which are 2, 3, and 4. So as a question, answer D belongs to what hydrogens on what carbon atom? Carbon 4. So it's a CH3 group. It has 2 neighbors. The n+1 rule gives you 3. So you see 1, 2, 3 lines. So that's going to be your CH3 group. And then C is the most complex because you have 6. Well, you have 5 neighbors. The n+1 rule is 6. Notice how it doesn't look very nice. And again, probably next week we'll talk about why these things don't look as nice as we think they should. There's another complicating factor that happens. You have a question over here? Where was the voice coming? You?
How do you determine the difference between A and D?
Between A and D?
It looks like A only has 3 keys.
Yeah, so A is a CH2. It has 2 neighbors, so it should also be a triplet, right? So this should be a triplet. The way that you tell the difference is by the chemical shift, because the chlorine is delta minus, and that carbon's going to be delta plus. So the heteroatom influences that chemical shift greatly, even though they're both triplets. There's another question.
Oh, I was just wondering, when you said like it has 5 neighbors, you has like 4 plus 1, right?
This one, so that CH2 group has 3 plus 2. So that's 5. Then you do the 1, so it's 6.
Oh, you're right.
So what he had asked is, even though they're both showing up as triplets, due to the neighbors, again, the chemical shift difference, the greater chemical shift difference is due to that heteroatom. That's going to push it, much past, 0 to 1.5 is where your normal sp3 hybridized carbon H's are. And so once you add a heteroatom, you're really pushing it past like 3 to 5.
Looking at the proton NMR, and there's always like one substance that they're basing NMR off, right? So a lot of times it's like methane and things like that.
Yeah, so you're, D is closer to looking like methane, which is upfield. And then as you move towards 10, it's downfield. So questions? Yeah. Yeah. Yeah, no, I just have to calibrate myself. I think it's downfield. I think upfield is towards 0.
So I looked at A and B, so it could be closer to that, like,
So with the last 15 minutes here, we'll essentially go through pulling out all of the data on this one slide, and the rest of the slides are just sort of the individual questions. So I call this putting it all together. So we have IR, mass spec, carbon-13 NMR, and proton NMR. So under the sticky note here was the molecular formula. So rather than giving that to you, we're going to piece it all together by extracting some information. And then from those little bits of data, we'll make fragments, we'll piece the fragments together and come up with a structure. Let's start with the IR. Does the IR speak to you? So there's some sort of oxygen. Can we narrow it down, get more specific? Carbonyl group in, I think I heard someone say carboxylic acid. Does that sound good? So we have a carbonyl group. Here at 1715. And those squiggly lines are fragments. So right now we know we have C and O. We also know that that's 1 degree of unsaturation due to the pi bond. This broad thing here, 35 to 2500, that's the OH. And so we know that those two things together make carboxylic acid. So already we have CO2H as a fragment in the molecular formula. So that's 1 degree of unsaturation. What can we say about the mass spec, where the parent ion is at 74? So it corresponds to the weight of the intact molecular formula. It's even. So there's no odd number of nitrogens. It's kind of hard to see, but when you look in there, there's no M+2. So we can eliminate bromine, we can eliminate chlorine. We can also eliminate bromine because bromine is 79. And everything together here is 74. So those are things we can just confirm the claim that we're going to propose here. So no chlorine, no bromine. Let's hop over to the carbon NMR. So I want to focus your eye here where it says proton decoupled. This is how a normal carbon NMR looks. So notice the shift from 0 to about 220. Don't worry about what it says proton decoupled. Any carbon data that I give you is going to look like this, just the single lines. The thing that says solvent, you just ignore. So when you're looking at this spectrum down here, how many signals do you count? So there's 3. So again, I want to frame this to you. When you're given the structure and you determine the unique number of carbons, It's essentially what you're doing here in reading that data. You're counting those signals. That's the unique number of carbons, so there's 3. See the signal down here at about 180? We already know from the IR that there is an sp2 hybridized carbon that's present in the carboxylic acid. So this signal here has to belong to that carbon. So we've already assigned one of the 3. And so we have 2 remaining. Now, if you look right above that, see where it says DEPT? It stands for a fancy name. All it is remember when I said the NMR is a giant magnet, and then you're pulsing it with radio waves? Radio waves can be like different wavelengths and stuff like that. That's all this is doing. It's hitting it with a different wavelength of radio waves. Notice the key. It says CH2 groups are down, so they're phased negative. If this is your spectrum, anything above is positive, anything below is negative. CH2 is down, CH3 and CH are up. So see the 2 signals stacked above it. What can we say about this signal here? What type of group is that? So it's a CH2 group, so there's another fragment. So far, if we revise our molecular formula here, now we have C2, total of 3 hydrogens and 2 oxygens. Then we have this 3rd signal here, which is phased positive. So the question is that a CH3 or a CH? And so the way that we can confirm that is now by looking at the proton NMR data. This thing from 12 to like 10 right here is a blow up. If we count that as a unique signal, how many total signals are there in the proton? So 1, 2, 3. It's kind of tiny, but it says this signal right here exchanges with D2O. Hydrogens that are bonded to heteroatoms will typically do that. And so we already know that there's an OH there. So that H of the acid belongs to this signal right here. And so for the other 2 peaks, to walk through the logic and make the assignments, we're going to use those numbers in blue. And so where did I get those numbers? Let's just say, see this line here? This little line that's above or on each signal. That's called an integration curve. So like back in the day when these things were plotted, that little curve would show up, you'd get a ruler and measure it in millimeters. And we'll just say that those numbers in blue are millimeter distances. What it's going to tell us is the ratio of those hydrogen sets to one another. And so what we do now is the smallest number there is 4, right? We're going to take everything and divide it by 4. So 4 divided by 4 is 1. 8 divided by 4 is 2. And 12 divided by 4 is 3. So the 1 hydrogen, that belongs to the OH. 2 hydrogens, that belongs to the CH2 group, which we got up from the carbon data. And then the last signal has to be a CH3 group. So these are the fragments we're dealing with. And now we basically have to stick them together so that we don't leave anything out. Meaning that the CH2 group has to be bonded to the methyl group and also bonded to the carboxylic acid group. And so when we do that, we get CH3, CH2, CO2H. And so the last sort of run of questions here can you tell how many lines are in this signal? Is there sufficient resolution? What? 4. And so when we do the assignments, we can say that that signal because it has 4 lines, the neighboring carbon must have 3 hydrogens. Does that make sense? So that has to belong to the CH2 group. Then this signal has 3 lines. It's a triplet, so it has to belong to the CH3 group. And so we'll write that in, we'll say quartet, triplet. We can say this is going to look like a quartet, and then that's going to look like a triplet. And so that also makes sense because the methyl group looks more like methane, so it has the smallest chemical shift. The CH2 has done 2 substitutions, so it should be further away. One minute for questions. So again, I hope you see that everything we've learned so far, it's building up on itself, so make sure that you're sort of clear on these concepts. I think in the Canvas webpage, the Notre Dame website has problems exactly like this, so you can practice that skill and get good at it. Don't forget to do your quiz.